There's points to
Absolutely not. Absolutely not.
All
No.
right.
If you miss 15, okay. 5, no.
What about 10?
I'd think about it. He'd have to make
How
a
many did I
donation to the
miss?
solar fund. Okay,
Yeah, that's how many I missed.
so here's the
Well,
next
yeah, let's
big
keep
unit,
it. That would not reason.
This nice.
and that's redox reactions.
On the brain, you know?
So, is that going?
Yes.
Okay.
I like this one.
So, hopefully you might have seen this in Chem 2, and if you haven't, it's not a big deal. So here's the bigger picture when it comes to basically the basic idea of redox reactions. Redox reactions boils down to a tug of war over electrons. Who wants the electrons more? Okay, that's it. Redox reactions is just that. So there's that aspect of it. The other side of it is that Mother Nature is going to allow a redox reaction to happen if Mother Nature ends up in a more stable arrangement that puts it at the bottom of the energy well. So if you see a redox reaction happen, something has more pull on the electrons than the other thing does, and Mother Nature goes to a lower energy state. That's it. If you keep that in mind, redox reactions aren't that tough. So redox reactions to a certain extent is like a bookkeeping thing. And the other thing that you want to keep in mind with redox reactions is the number of electrons lost equals the number of electrons that are gained. That's it. I can't have a manganese electron or a manganese atom gaining 5 electrons and then oxygen losing 2 electrons. Okay, it doesn't work. So electrons lost has to equal electrons gained. So there's different ways that you can do this. But I always like Leo says GER. Okay? So if you lose electrons, that's oxidation. If you gain electrons, that's reduction. So you can always tell when kids are taking a redox test, because you walk around and kids are going, okay? You can always tell. You can always tell if they're taking a magnetic test with the right-hand rule because they're doing this in the air. So if you know what to look for, you can walk by and kind of tell, oh, what test are the kids taking? Oh, magnetism. Oh, Leo says girl. Oh, they're taking a redox test. So let's start with a simple example. So I'm going to take some 1 molar hydrochloric acid and give that a pour. And then I'm going to drop a piece of magnesium in here. So the other thing that's going to become your friend is on the back side of your periodic table is the standard reduction chart. So get this out so you can kind of begin to familiarize yourself with this. So what's important about this chart is that it's a reduction chart, okay? You could easily have an oxidation chart, but everybody talks about it from a reduction standpoint. So let me kind of get you used to this idea. The reason that all of these are reduction equations is because they're all gaining electrons, okay? So if you look at the bottom one, way down here at the bottom, you have lithium plus an electron forming elemental lithium. Up at the top, you have fluorine gas gaining an electron and forming a fluoride ion. So if you look on this trend, a couple of things to notice. Sometimes you gain electrons and you form ions. Sometimes you gain electrons and you form the elemental form of the substance. Like for example, Ag plus, that will use a lot of silver. So Ag plus tends to gain an electron and form Ag solid. You could also gain electrons and form ions, like Cr3 plus can gain an electron and form Cr2 plus. So what's common to all of these is that, and this sounds fairly biblical, but as they are written, they're all reduction equations, okay? They're all reduction equations. Now, This number over here to the right, it's called E naught, okay? And that stands for your standard reduction potential measured in a unit called a volt, okay? So a volt is measured in what we call joules per coulomb. Joules is a measure of energy. Coulomb is a measure of charge. So when you look at these E naught values, if you look up here at fluorine, okay, notice that's 2.87, and that's a positive number. Down here at the bottom, you have lithium, and that's a negative number. The middle ground is hydrogen, where you have 2 H plus 2 electrons forming elemental hydrogen. So basically what we did is we said, okay, we're going to establish hydrogen as the baseline, and we're going to call that 0. So that's like the reference point. So we're going to spend a lot more time talking about it. I'm just laying out the initial salvo on this idea. So the more positive the bigger the positive number is, the more it wants to go in the direction as it's written. So what this means is that if you look up there at the top, fluorine gas really wants to take in electrons and form fluoride ions. Okay? It really wants to do that. Fluorine's going, oh my God, I need electrons. Ooh, okay? Now, down at the bottom we have lithium gaining an electron, lithium ion forming gaining an electron and forming elemental lithium. They're like, whatever. If it happens, great. I'm not going to put any effort into this thing. So the bigger the positive value is, the more it wants to go in this direction. The more negative the value is, the more it wants to actually go in the reverse direction. Okay? So we're going to spend so much time talking about this chart. I'm just trying to paint for you the overall picture. So what we're going to do is that I'm going to take a piece of magnesium, and I'm going to put that into hydrochloric acid, and I'm going to get magnesium chloride and hydrogen gas. Okay? So there's your basic Chem 1 equation. Elemental magnesium is going to react with hydrochloric acid. We're going to get magnesium chloride and hydrogen gas. Okay? Boom, there you go. Standard, boom, it's balanced. Chem 1, whoo, I'm a chemistry student. I can balance the equations. Good for you. Okay? Now, there are rules that go with redox reactions. One of the things you have to keep track of is called the oxidation state. So positive oxidation states means like it's a cation, means that it's lost electrons. Negative oxidation states, oddly enough, means that it's gained electrons. So when you talk about, for example, fluorine becoming 2F minus, okay, the oxidation state of fluorine is 1 minus. So that isn't a big deal. The issue kind of comes when you have the elemental form of the substance. When you have the elemental form of the substance, which in this case is magnesium, so any element that's by itself has an oxidation state of 0. Okay, it's not written, but it's just implied that it's 0. So when you have the elemental form of anything, magnesium, hydrogen, oxygen, whatever it is, if you have the elemental form of anything, the oxidation state is 0. Mainly because it's just that. Okay? It's just magnesium. It's just hydrogen. It's just gold, whatever it is. Okay? It hasn't lost electrons. It hasn't gained electrons. Everybody's just chilling out. Oh, a bunch of magnesium atoms, right? No one's going to take electrons from the other one. Okay? It's kind of this commune thing, right? Oh, we're a bunch of magnesium, atoms living in harmony and peace. Okay? No one's going to take electrons from anybody else. So here's what's going to happen. So I have this chunk of magnesium with an oxidation state of 0. It has electrons. It has 12 of them to be exact. But it just hasn't gained or lost any electrons. It's just a 0. Okay? Now, we have hydrochloric acid. Now, here's the deal with hydrogen. 99% of the time, what's going to happen is that hydrogen is going to have a charge of 1 plus if it's bound up with anything else. And this is what you already know. Oh, hydrogen has a charge of 1 plus. It's a hydronium ion, right? Which basically means that how this started, it started with a proton and 1 electron that was going around it. And basically the electron said, I'm outie. It left. The only thing that was left behind was that proton. because the electron bugged out. Okay, so an H plus is literally just a proton if you think about it. It's a single proton, that's all it is. Now the chlorine is sitting over here, and it has a charge of 1 minus because it's gained an electron. It has 7 valence electrons. It wants 1 more. It gains 1, it becomes 8 electrons. When I was teaching in Africa, I would explain this in terms of goats. Everybody wants 8 goats. Fluorine or chlorine has 7. How many more does it want? Teacher, it wants 1 more. Right, it's going to gain that extra goat. Now it has 8. Everybody's cool. Hydrogen only had 1 goat. Really didn't like the goat anyway, so the goat runs off and the proton doesn't care because it's just 1 goat and who really cares, okay? So it lost a goat, it gained a goat, so you can think of redox reactions in terms of transfer of goats. So when I was in Africa, I taught this in terms of who gets the goats, who wants the goats more. So magnesium sitting over here, it has 12 goats and it's cool, right? Hasn't lost goats, hasn't gained goats, boom. Hydrogen has lost a goat, chlorine has gained a goat. Everybody's cool over here. And I know that's stable like this because of the fact that if I look at this, oh, here's a piece of magnesium ribbon. This is stable. If it wasn't stable, it wouldn't exist as magnesium. So if you look at how magnesium is formed, magnesium forms a little bit of lesson in astronomy. Magnesium wasn't formed at the beginning of the universe. Okay, there was no magnesium atom. So basically there was just hydrogen. Hydrogen formed into helium. You got a little bit of lithium thrown in. First generation of the stars began to collapse. Then you began to form like the heavier elements, nitrogen, oxygen. Okay, those collapsed. Then you began to form magnesium. So all of these magnesium atoms, and there's a lot of them, in this magnesium ribbon, they've been through a lot. Okay, they were formed in the collapse of stars. That magnesium then got scattered out when that star collapsed and exploded, went supernova. It got scattered out. The universe, for whatever reason, began to say, okay, hey, let's reform you guys into something else. So this strange rock formed, third one from our star. And this magnesium atoms, some of them we had higher pockets of them. So we went through and we mined them. We separated out the magnesium atoms, said, okay, hey, all you magnesium atoms come over here. And they got that. And then we stretched it and we formed it into this ribbon, okay? So these magnesium atoms and their electrons have been through a lot, okay? Formed in the depth of the star, got kicked out into the universe, reformed, processed, here they are. They've been sitting in that drawer for God knows how long. They're tight, okay? They've been through a lot together, a lot, okay? Then you have hydrochloric acid. That's pretty stable, right? It isn't like we have to worry about hydrogen HCl, hydrochloric acid, exploding. It isn't like, oh, don't let the hydrochloric acid in an open flame. Okay, it's stable, right? Stable. So here's what's going to happen. I'm going to take this piece of magnesium, I'm going to drop it in the hydrochloric acid. So on an atomic level, here's what's going to take place. So here's this nucleus, has 12 protons, and around it, it has 12 electrons. There's the hydrogen, okay, which is just basically nothing but a proton. And then you have the chlorine over here with the 8 goats, okay? Now, the chlorine isn't going to be part of the story because the chlorine is sitting there going, I got the 8 goats, I'm cool. I don't need anything. You guys just knock yourselves out. So the hydrogen is going to come along to the magnesium and go, mind if I take one of your electrons? The magnesium needs to make a decision. It says, well, I can hold on to those electrons because we've been through a lot together, you know, deaths of stars, reprocessed, you know, we've been through a lot. Kind of attached to it. Okay, so that's option number 1. The magnesium decides, I like the electrons, and no, you can't have them. The other option is the magnesium goes, you know, I got those 2 electrons way out there on that outer valence electrons, okay? Eddie and Edna, these 2 electrons are just a pain. They're annoying, okay? All they do is bicker, okay? So really don't like them. And it's going to say, you know, screw it, take them. I don't care, okay? Yes, we've been through a lot together, but really, I'm not that emotionally attached to them. So if this reaction is going to take place, and it is, basically the magnesium atom says, hey, take the electrons, I don't care, okay? I'm going to be happier without them. The hydrogen is going to sit there and go, score! Okay, I'm going to get an electron. Now, a couple of things happen when that proton gets that electron. Not only do you form hydrogen gas, okay, with a proton and an electron, then another one comes along and says, oh, hey, let's be besties, let's be twinsies, it's like twin day, right? So then a single hydrogen atom isn't very stable. So what it does is it goes along to another one and says, hey, you and me, let's hook up. So a couple of things happen. The proton comes up to the magnesium and it says, hey, yo, electrons, got an electron to spare? It says, sure, take one. Eddie, Edna, you're out, okay? So now they're down to 10 electrons. They've lost 2. There's 2 out there in the valence electrons. Polly and Bubba, the 2 protons, take in the electrons, and then they're not stable, so then they overlap their electron clouds to form hydrogen gas. So this is a classic redox reaction. And it happens because Mother Nature becomes more stable. So if you look at what's going to happen here, so if you come down here, and on this reduction chart, you have magnesium. So Mg2 plus 2 electrons turns into magnesium. That has a value of negative 2.37. So what you'll see is that that big negative value tells me that, Mother Nature really doesn't want to go in that direction. Mother Nature wants to flip this thing over. So what happens is that magnesium wants to reverse this reaction. It wants to lose its electrons, even though magnesium is cool, right? It really wants to give up 2 electrons because it's going to become more stable. Now, you notice that hydrogen is up here with a value of 0 because that's like the benchmark. So what you'll see is that the magnesium gets flipped over and it goes from negative 2.37 to positive 2.37. Check my math, and this will make sense later. If I take a positive 2.37 and add that to 0, I get 2.37. So my overall E naught value is positive value. And what you see when you have positive E naught values, that means the reaction is spontaneous and it's going to take place. So what's going to happen is that we take this and where'd it go? Here we go. I got this, my magnesium ribbon. I drop this in there, boink, okay? And right away we start this kind of violent reaction, right? You've all seen this before. So what's happening is that all on an atomic level, these protons are coming up to the magnesium and going, give me your electrons. It goes, got it, right, we're out. Then you're forming this hydrogen gas, right? And so that hydrogen gas, and that's what you're seeing as the bubbles. So, and it's also very warm. You'll see that this is an exothermic reaction. So I'm going to take some of this, and I'm going to collect some of that hydrogen gas. Okay? Now, Skippy, I'm going to need you to hold that.
Uh-oh.
I got faith in you, man. Okay? A little bit of faith, not a whole lot, but just a little.
Is
Okay?
this demonstration going to involve any fire?
It is. So this is actually very, very warm because what's happening is that it's giving off energy. We'll get into thermodynamics later. So, you got that? Okay? So now, I'm going to light that. Okay?
How loud does this want to be?
We have made fire.
Good.
Now,
Thank God.
okay? Now, I'm going to put this down here. Okay? And then I'm going to take this, put that in there. Woo!
That was loud.
That was a good one, right?
And Morella jumped.
Okay? So we made the test, it's called making the test tube bark. Okay? That sounds like a little chihuahua. So, what we just did is actually 2 different redox reactions. So, how this took place is the magnesium lost electrons. So the magnesium, and some people like to look at this in terms of like a number line. Where here's 0, plus 1, plus 2, plus 3, and then negative 1, negative 2, negative 3. So the hydrogen started off at plus 1. Okay, so here's where the hydrogen started. Hydrogen started off at plus 1. Now, we formed hydrogen gas, and we can always tell that we formed hydrogen gas because if you make the test tube bark and you get that sound, oh, you generated hydrogen gas. So we went from H1 plus, and then we gained an electron, and this is actually going to happen twice because I know that I produce H2. So the hydrogen gained an electron. So is the hydrogen reduced or oxidized?
Reduced.
Reduced. Why?
Because GER.
That was the most intelligent explanation I've ever heard in my entire life, because of
Thank
GER.
you.
How about this? Did it gain an electron?
Yes.
Yes, so therefore it was
Reduced.
reduced. So this stays in the direction that it's written. So if you look at that reduction chart, this is going in that direction. So this is reduced. Okay? Now, we went from H1 plus to 0 because we're forming elemental hydrogen. So elemental hydrogen has an oxidation state of 0. Okay? Now, where did the magnesium start?
0.
The magnesium started at 0, and it ended up at 2 plus. So the magnesium went in this direction. So the magnesium went from an oxidation state of 0 to an oxidation state of plus 2. So therefore, it was oxidized because it lost electrons. So notice that, so if you're a number line kind of person, okay, and some people like this. Here's magnesium at 0. It moved to the right, okay, because it lost electrons. So if you like number lines, oh, I started at 0, I ended up at plus 2. That was oxidized. The hydrogen went from 1 plus and it gained an electron and went back to 0. So here's the other thing. We always have redox reactions. We don't have re-re reactions and we don't have ox-ox reactions. Okay?
Super Bowl.
Huh?
Riri.
Halftime show.
Oh, ask me, I dare you if I care.
Berg, do you care?
It's like
What's your
Rihanna?
gut- we've been together for a while. What's your gut feeling?
I feel like you'll watch it.
I feel like it's super.
Oh my God! I have never watched
I
it.
felt like we
Yeah.
were Rihanna so
You get George Strait, Garth Brooks. Hey, I'll watch it. Okay.
Yeah, who?
Otherwise, no.
Bird Umbrella would blow your mind.
We need to get Tom Holland to do it.
Who would play
What's
this?
Umbrella?
Umbrella.
Who's Umbrella?
I didn't know what it
Rihanna's
was.
song.
Who's Umbrella?
Yeah.
I thought that was like an
Or what is
artist. I was like,
Umbrella?
I've never heard of them.
Okay.
Looks like an umbrella.
So, look at what happened when you took the hydrogen gas, right, Skippy? We took hydrogen gas and oxygen gas. Okay? So when I collected the hydrogen gas, I put the flame in there. And out of that, what did we get?
H2O.
Oh, H2O. Is this going to be a redox reaction?
Yes.
Yes, most definitely. So what's the oxidation state of hydrogen as elemental hydrogen?
0.
0. What about oxygen?
0.
So the air that you breathe right now, you all are breathing in all of this oxygen, okay? Oxygen gas. That has an oxidation state of 0. It's stable, right? It has all the goats that it needs. It's cool. It's just oxygen. It's diatomic because it's more stable that way. Now, when you produce oxygen in a compound, the golden rule is that oxygen is always 2 minus, except for one exception when you have hydrogen peroxide, H2O2. That's the only time that it's 1 minus. Look at you.
I said that before you. So.
Huh?
You
I
should
said
see.
I whispered it to Jenna.
Okay, that's
She
impressive.
did. I agree.
So every other time, oxygen is 2 minus. Okay, so that's like the anchor. Always start with oxygen being 2 minus. So oxygen here is going to be at 2 minus. So what's the oxidation of hydrogen going to be?
Plus.
Now, here's the
Plus
deal.
1, I would say.
Everything, water is electrically neutral, right? So when I add together the oxidation states of hydrogen and oxygen, they have to add up to equal to 0. So what plus -2 equals 0?
2.
Plus 2. But I've got 2 of them, so each one has a charge of
+1.
plus 1.
I ate no crumbs.
Wow. You went for it.
Okay? Now, so which was oxidized and which was reduced? The oxygen went from 0 to
Reduce.
2 minus. So did the oxygen gain electrons or lose electrons? It gained an electron. So therefore the oxygen was GER. Therefore the oxygen. So here's the dichotomy.
Lost this whole time. No, it's
Dichotomy.
Is that oxygen gains electrons, but it's reduced, and you would think, oh, it's oxygen, it should be oxidized, okay? Oxygen isn't, okay? Oxygen actually gets reduced. But it becomes an oxidizing agent because oxidizing agents contain what is reduced. So that's where we throw the oxygen into that whole deal. Now, what about the hydrogen? Hydrogen went from 0, what did it do? What did the oxygen do? Leo.
It lost electrons.
It lost an electron. So basically what happened is the oxygen comes up to the hydrogen and goes, I got 6 goats. How many does the oxygen want?
2.
It has 6 goats.
2.
Wants to gain 2 goats to end up with
8.
8 goats. So the oxygen is the big atomic bully when it comes to electrons. It comes up and it says, yo, let's have the electrons. The hydrogen goes, fine, take them. I just don't want any trouble. So the hydrogen gives up that, right? And now you, oddly enough, now you form this cool polar molecule of water, which is one of the reasons that we're here having this discussion. Because oxygen gains those electrons, so it has a negative end. The hydrogen gives up those electrons, so that's the positive end. It becomes very polar. It's a great solvent. It's a liquid at room temperatures. It has a relatively high boiling point and relatively low freezing point. Which is kind of cool, which is one of the reasons we're here. So imagine this. On the Fahrenheit scale, water freezes at 32 degrees. What if water froze at like 50 degrees?
Oh, that'd be crazy.
Wouldn't be why.
Right now.
You'd have a lot more snow. Unfortunately, Canada, probably even down here, would be a chunk of ice at this point. Okay? Because you'd have much bigger polar ice caps because you'd have a lot more ice. Okay? What if water boiled at, say, 50 degrees Celsius?
Oh, Celsius.
Arizona would just occasionally boil.
Water would occasionally boil. Yeah. Okay? So it's good that water has the properties that it does. Okay. Now, to do redox reactions, one of the most important skills you have to have is to be able to determine the oxidation states of atoms in compounds. Okay? So let me give you an example. So let's say that we're going to deal with nitrates a lot. So nitrates overall have a charge of 1 minus. So one of the things you've got to be able to do is figure out the oxidation state of everything within that nitrate. So start with this. Start with the anchor. What's going to be the oxidation state of oxygen?
-2.
So each one of these is going to be -2, but I'm going to have 3 of them.
-6.
So this whole thing has a charge of -6. So blank, this is an algebra problem. So x plus -6 equals 1 minus. So what's the oxidation state of nitrogen?
X equals 5.
Plus 5, right? So if I take 5 plus -6, I'm going to get -1. Now, here's what I want to caution you about. This concept of oxidation states works beautifully, okay? But it's more of like a bookkeeping, especially when you get into like carbon, nitrogen, because they have like 4 and 5 valence electrons. So we'll talk about nitrogen maybe in this case having an oxidation state of +5. That doesn't mean that nitrogen here has actually given up all 5 of its electrons. How many electrons does nitrogen have to begin with?
7.
7, okay? I doubt it's like you have 5 goats. you're not going to lose all 5 goats, okay? It's bad. You could, but I don't recommend it. So when we say that thing has a charge of +5, it's a bookkeeping thing. Now, but when we talk, and here's the weird thing, is that when we talk about oxygen having an oxidation state of 2-, that legitimately means oxygen has gained 2 electrons. So sometimes that actually physically means this is what this thing is doing. Potassium has an oxidation state typically of 1+, because it has 1 valence electrons. So sometimes when you look at those oxidation states, that's what's actually happening. It's gaining 2 electrons. It's losing an electron. But sometimes it's more of like a bookkeeping thing. It works, okay? So let me give you another example. So let's say that you have NO2, 1-. So you have nitrate, and then you have nitrite. Remember, 8s always have more oxygens than the ites do. So if I want to figure out the oxidation state of everything in a nitrite, start with the oxygens, right? So you've got 2 oxygens, each of those at -2, which gets you to -4. So here the oxidation state of nitrogen is +3. Because that way everything adds up to -1. So sometimes nitrogen is going to have an oxidation state of +3. Sometimes it's going to have an oxidation state of +5. It depends on what's bound up with. Now if you look at carbon dioxide, y'all are breathing out carbon dioxide right now. Okay, that's a good thing. Don't feel bad. It's like, oh, I'm breathing out carbon dioxide. It's okay. That means you're alive. Okay? You're breathing out carbon dioxide. Now, does carbon dioxide have an overall charge? Does carbon dioxide, the molecule of carbon dioxide, does that whole thing overall have a charge?
No.
It's completely neutral. So molecular forms of things have an overall oxidation state of 0. So everything here has to add up to 0. Start with the oxygen. Okay? So you have 2 oxygens, each of those at,
-2.
so that's going to be -4, right? So therefore, in carbon dioxide, carbon is going to have an oxidation state of +4. Okay? Now, if you have carbon monoxide, okay, in your homes you might have carbon monoxide detectors, okay? Huh? Yeah, because it forms a terminal bond with the hemoglobin in your blood, and then you can't do oxygen exchange. which
Isn't
is
that what
bad.
comes out of your car?
Yeah.
Yeah,
Oh,
I
and
saw a
carbon
movie where
dioxide.
they like killed themselves. Oh wait, that's
Yeah, they use your clothes.
yeah.
Okay.
It was like a horror movie.
Now, if you have carbon monoxide, what's the oxidation state of the carbon?
Probably still +4.
No,
+2.
because oxygen is -2, carbon here is +2. Okay? So even carbon can have different oxidation states based upon what you have. Now, one of the ones we will use most often, we're going to use this again and again and again, is the permanganate ion, which is MnO4, 1-. So I want to make sure everybody's cool with this because we're going to use this a lot. Okay, we're going to do an entire lab on the titration of potassium permanganate. Potassium permanganate is cool because it has a very, very deep, vibrant purple color. So we need to figure out the oxidation state of manganese. Now, if there's ever an element on the periodic table that has an identity crisis in terms of its oxidation states, it's manganese. Because literally, manganese can be 7 + 6 + 5, 4, 3, all the way down to 2. So depending upon what manganese is bonding with, you can have completely different oxidation states. But this is the one that we're going to deal with most often. Okay? So everything here needs to add up to -1. So the oxygen has 4 of those, start with that. So the oxygen is going to have a total charge of -8. So therefore the manganese has to have a charge of +7. So a manganese in a permanganate ion has an oxidation state of +7. So what that means is that permanganate is like, man, I have lost 7 goats. This is bad. Okay? So what manganese is really wanting to do is take in electrons, okay? Because it has this huge deficit because it's lost its goats. So it's going to go up to everybody else and go, hey, can you help a brother out? I'm kind of down on my goat luck, man. And so, yeah, it's going to give us your goats. Exactly.
Give me your goats for right now.
So, because permanganate really wants to take in electrons, is it really willing to be oxidized or reduced? It wants to take in electrons.
Good.
My God. Articulate words, people. You have words. Use them. Grrr. So, you can write that on the test, so help me. I'm just going to flunk you. So, what does the manganese want to do? Take in electrons, right? So it wants to be reduced. So therefore, is it an oxidizing agent or a reducing agent? It's an oxidizing agent because remember, oxidizing agents contain what is reduced. So this is why when you look in your chemical storeroom, guess what? We keep potassium permanganate and all of the ones that are good oxidizing agents, we keep them completely separate. Because if you put them with good reducing agents, guess what? Chemical reactions happen and bad things can happen if you're not under a controlled situation. So this is why we keep oxidizing agents separate from reducing agents. So that way we don't have to let them mix it. Okay, so stop yonder camera.
No, stop yonder camera.
Oh, sorry.
If that's like this.
So this is the most important skill you have to be able to do redox reactions, and that's be able to assign the oxidation states of the different chemicals in compounds. So up there, for example, on you have sodium sulfate, Na2SO4. And I'm asking you to particularly figure out what's the oxidation state of sulfur in sodium sulfate. So here's the deal. Start with your oxygen, okay? Start with the oxygen. Oxidation state of oxygen is always going to be -2. And I've got 4 of those, so that gets me to -8. Now, there is no charge overall on this thing, so I want everything to add up to equal to 0. Okay? Now, start with your sodium. Where is sodium at on the periodic table?
The first one.
It's an alkali metal. How many valence electrons does it have?
1.
1. So is sodium going to lose 1 goat or gain 7 goats? It's going to lose a goat. Okay? So you have 2 of those, so the oxidation state of sodium is going to be +2. So +2 plus X plus -8 adds up to 0. So what's the oxidation state of sulfur going to be? +6. Okay? So sulfur is going to be +6. Now, where it gets a little weird is, let's say, for example, you're going to look at on G where you have the sulfur in the H2S2O7. So you got H2S2O7. So this is this big complex molecule. What do you want everything to add up to? 0. So you have 7 oxygens each, so that's going to be a total of -14. Now, hydrogen almost always is going to have an oxidation state of 1+. It's going to lose that 1 electron. Okay? So if I take that hydrogen and it's going to lose an electron, and I've got 2 of them, what's the oxidation state of my hydrogens then? Total is going to be +2. So I want everything to add up to equal to 0. So basically, I got +2 plus X plus -14 adds up to equal to 0. So what's the total charge the sulfur has to have?
+12.
+12. But there's 2 of them. So each sulfur is going to have a charge of plus 6. So, yes,
Will there ever be cases that we have to deal with in which the same atom, different, like if there's
it
two
gets
sulfurs,
oxidized
there's
and reduced?
well, like one sulfur has a different charge than the other sulfur or
No.
something like that?
No. But sometimes you have situations where the same element gets oxidized and reduced in the same reaction, but that's very rare.
That's not.
No, I'm just telling you. Okay, so try, and we'll go over this, so just do a little practice right now. Try and do A through J and figure out what those oxidation states are. Gracie, can you reach over and stop that? Yes. So on the reduction on number 1, okay, it's going to be, you're going to start with MnO4, and it's going to turn into Mn2 plus. Okay, so if you figure out what's being reduced and what's being oxidized. So this Mn is sitting here at 7 plus, it turns into Mn2 plus. So the only way that can happen is if it gains 5 electrons. So over here, I'm going to put 5 electrons. Okay? Now, I've got 4 oxygens. I also have to balance the oxygens. I balance the oxygens by adding waters. So I'm going to put 4 waters over here. Okay? Now, flashbacks? Now I got 4 waters. But now I have 8 hydrogens. These are in acidic environments. So I'm going to come back over here and I'm going to put 8 hydrogens. Now, here's how you can tell that you got this right. If you add together all the oxidation states on both sides, they should equal. You should balance on charge and number of particles. The oxidation state on this one, the oxidation part of this is going to be H2SO3 turning into HSO4 with a charge of 1 minus. So in this situation, what you'll see is that the sulfur is being oxidized. Okay? So what I'm going to do, I'm just going to tell you what your answers are so you can work this out. So here's your overall answer on the final equation. So on number 1, here's what it is. 2MnO4 plus H plus 5 H2SO3 is going to yield 2Mn2 plus 5 HSO4 minus plus 3 waters. So if you do that one right, that's what you're going to get. And then the last one on number 2, 14H plus Cr2O7, 2 minus, and I hate Wednesdays. That's an arrow. So those are your 2 answers for the 2 problems. So that's how you can tell if you got them right.
Nice. Oops.
So